Hey everyone, welcome back. You know those deep dives you keep asking for? Well, this one's all for you. We're tackling the grand Fibonacci SMF RVS theory, and let me tell you, this one's a doozy.
Oh yeah, it's ambitious to say the least. A real theory of everything contender.
That's right, claiming to explain it all from tiny atoms to giant galaxies, and get this, maybe even why we haven't met any aliens yet.
Wild, right?
Totally. Now, you sent over excerpts from a research paper laying it all out, and I gotta be honest, it dives right into the deep end.
Yeah, the physics gets pretty complex pretty quickly.
So let's break it down for everyone, starting with the three core ideas this whole thing is built on.
Okay, sounds good. So first up, we've got something called subtle magnetic fields, or SMFs. And these aren't like your everyday magnets, sticking to the fridge.
Haha, so no fridge magnets involved in this theory. Darn.
Nope. Think of SMFs as like higher dimensional magnetic fields, and they actually interact with the very fabric of space itself.
Okay, so shaping space itself. Got it. What's the second idea?
All right, so the second one is called the relative vacuum of space, or RVS. Now, when we say vacuum, most people think empty, nothing there. But according to this theory, the vacuum isn't actually empty.
Oh, I've heard this before, like it's this seething sea of energy or something.
Yeah, you got it. It's more like this constantly shifting sea of energy. And guess what? Those SMSs we talked about, they're always interacting with it, creating these pushes and pulls within the RVS.
So it's dynamic, always in motion. I guess that's where the relative part comes in, right? It's all relative to those SMFs and how they're influencing things.
Exactly. Now, for the third piece of the puzzle, and this is where things get really wild mathematically, it's called Fibonacci fractal scaling. And it basically describes how the same patterns repeat at different sizes no matter how much you zoom in or out.
Oh, like fractals, those trippy images where you keep seeing the same shapes no matter how much you magnify them?
That's the one. And the paper argues that this scaling applies to, well, everything, from the way atoms are structured to how planets orbit stars, and even the large-scale structure of the entire universe.
Wow, so linking the tiny to the massive, I'm starting to see how they're trying to build a theory of everything here.
That's exactly it. And the coolest thing is, it's not just like a vague, oh, they look kind of similar. There are actual equations they've developed
Yeah.
showing how a push force remains the same even as you change scale. Like, no matter how big or small you go, the same fundamental forces are at play.
Okay, I'm going to trust you on the equations for now. But the takeaway here is that there's math backing up this idea of linking things across wildly different sizes. And that leads to something they call nodes, which is where this theory gets really interesting, at least for me. They're saying this can explain why we see stability at certain sizes or distances. They talk about atomic nodes and planetary nodes. What's that all about?
Yeah, great question. Let's start with atoms. You familiar with magic numbers in atomic structure? Like certain numbers of protons and neutrons that make atoms super stable?
Oh, yeah, like helium with its 2 protons, or oxygen with 8.
Yeah.
They're like the VIPs of the periodic table. Everyone wants to be as stable as them.
Exactly. But for the longest time, we've just kind of observed it without a solid explanation for why these magic numbers exist. This theory suggests it's because of those SMFs interacting with the RVS. They create specific spots where the vacuum density is higher or lower.
Like little pockets of stability in the vacuum itself.
Yeah, exactly. These nodes, they act like wells of stability.
Hmm.
So if an atom happens to have a config that fits right into one of those nodes, boom, it's way more stable because it's in this sweet spot where all the pushes from the vacuum kind of balance out.
Okay, so it's not just random chance that some atoms are more stable. There's a deeper reason based on this SMF-RVS interaction. I like it,
Yeah.
but how does this node thing apply to something as huge as a planet?
Well, the idea scales up, remember. The distances planets settle into from their stars, those aren't just random either. They tend to gravitate towards orbits where that cosmic push from the SMF-RVS interaction is balanced. Those are your planetary nodes.
So finding their own magic number distances where everything's in harmony, just like those super stable atoms, it's starting to paint a picture of a universe where everything's connected in a way we never really imagined.
Yeah, like a cosmic harmony playing out across all these different scales. And you know what's even more interesting? This can actually tie back to an old astronomical idea called the Titius-Bode law. Remember that one?
Vaguely. It was about trying to predict planetary distances.
Exactly.
Yeah.
And it wasn't perfectly accurate, but it kind of worked. And the grand Fibonacci theory might explain why. Like, there was a reason it was kind of right, even if we didn't have the full picture of this push-based gravity influencing orbits back then.
Wow, so connecting new ideas to old ones. That's pretty cool. Okay, so we've got SMFs influencing the RVS, creating a push that results in these nodes of stability, both at the atomic level and the planetary level. But where does gravity fit into all of this? I mean, it's kind of a big deal when we talk about planets and galaxies, right?
Oh, absolutely. And this is where the grand Fibonacci theory throws us a real curveball. See, most of us picture gravity as a pull, like this force coming from massive objects drawing everything towards them.
Yeah, that classic bowling ball on a trampoline analogy,
Yeah.
warping space-time and making everything roll in.
Right. But what if, and this is a big what if, we've been thinking about it all wrong, what if gravity is actually a push?
Hold on, a push. That seems totally backwards. You're saying instead of being pulled towards those massive objects, we're being pushed towards them by something happening in the space between. How does that even work?
It's a big shift, I know. But the idea is that gravity is actually a result of the interaction between the SMFs and the RVS. Like the variations in vacuum density, influenced by those subtle magnetic fields, create a net outward push.
Okay, I'm trying to wrap my head around this. But if gravity is a push, wouldn't everything be flying apart? How does anything stay together?
Yeah, it's a great question. And it gets to the heart of the complexity here. Remember those nodes of stability. Those are key to understanding how a push-based gravity can still result in both attraction and stable structures. It's about the interplay of forces across different scales, finding that balance where things don't fly apart or collapse in on themselves.
So a cosmic dance of pushes and pulls from the SMF-RVS interaction, combined with those fractal patterns and nodes, creating the conditions for stability and attraction. It's a whole new way of looking at gravity.
Absolutely. And what's really mind-blowing is this push model, as strange as it sounds, actually leads to the same gravitational effects we observe in the universe. Like, as you move further away from a massive object, the density of the RVS between you and that object decreases, reducing the push.
Yeah.
And guess what? That reduction follows the same inverse square relationship we see in Newton's law of gravity.
So they've done the math, and it actually holds up. That's pretty impressive. But if it's right, we need to rethink everything we thought we knew about gravity. And it makes me wonder, if we got gravity wrong all this time, what else are we missing? What other secrets are hidden in the universe?
That's a great question to ponder. Maybe we're just scratching the surface of understanding how things really work. But we'll save those big cosmological questions for later. First, there's another mind-blowing implication of this theory we need to dive into. Alien life.
Yes, that's what I'm talking about.
Yeah.
This theory actually has something to say about why we haven't met any extraterrestrial tourists yet.
Oh, it does, and it's a fascinating take. But we'll save that juicy tidbit for the next part of our deep dive.
I can't wait. Okay, so we've laid the groundwork for this wild grand Fibonacci theory, right? SMFs, RVS, fractal scaling. It's a lot to process. But now, let's get to the fun stuff. Aliens. Because this theory, if it's even partially on the right track, could explain why we haven't bumped into any extraterrestrial tourists yet.
It definitely gives us a new perspective on that whole question. And it all comes back to those magic numbers and nodes of stability. The things that make certain configurations stable, whether we're talking about atoms or planetary orbits.
Right. Those sweet spots where everything's in balance, created by that SMF-RVS interaction. So you're saying this cosmic harmony could extend to life itself?
That's the implication. Think about it. Life on Earth, it evolved to be stable within our specific SMF-RVS environment. The arrangement of those nodes, how the vacuum's pushing and pulling, all that creates the conditions for our kind of life to, well, exist.
Well, like our solar system's got its own cosmic recipe for life, baked right into those fractal patterns. Okay, I'm with you so far. But how does this relate to aliens?
Okay, so picture this. A civilization evolving on a planet and a totally different star system. Now, their star system might have slightly different magic numbers. You know, their SMF-RVS environment would be a bit different, leading to different nodes of stability.
So different atoms, different planets, different...
DNA.
Whoa, their DNA would be different too.
Exactly. Their DNA would have evolved to be stable in their unique environment, not ours. It might be similar, sure, but not exactly the same. And that's where things get interesting. Or maybe kind of scary.
Scary how? Lay it on me.
You know, this difference in magic numbers, it could mean that aliens from other star systems, if they try to visit us, they might literally fall apart.
Wait, what? Like disintegrate? Poof.
Haha, maybe not that dramatic.
Right.
But their biology might just not be compatible with our environment. Their DNA wouldn't be as stable here. Their cells might not function right. Their whole physiology, you know, everything that makes them them, it could start to break down because they're just not in the right SMF-RVS groove.
So showing up on Earth would be like going to a party with an atmosphere you're allergic to. Not a great vacation.
Exactly. A major obstacle to interstellar travel. Even with super advanced tech, you can't escape the fundamental laws of physics, or in this case, the influence of those SMFs and the RVS.
It's like having the wrong software, right? It just won't run on a different system. So it's not just about the distances between stars being huge. It's about this potential biological incompatibility.
Exactly. And it might not even be a one-way street, right? We could be just as vulnerable if we tried to visit their planets. We're all kind of stuck in our own little cosmic bubbles, each with our own unique magic number setup.
So maybe that's why we haven't found any solid evidence of aliens yet. It's not that they're not out there. It's just that the conditions for actually meeting up and, shaking hands or whatever aliens do are super rare.
It's a compelling possibility, right?
Yeah.
This theory isn't saying we're alone in the universe, but it does suggest that finding someone who can actually handle our planet's, well, vibes is a long shot.
Like, the universe is saying, sure, there might be other life, but good luck finding someone who can hang out with you on your weird little planet. It makes you think about how special, how unique our little corner of the cosmos might be.
Totally. And all this hinges on these seemingly abstract concepts, right? SMFs, RVS, fractal patterns.
Yeah.
It shows you how everything could be connected, from the tiniest particles to those grand cosmic structures, and even the potential for life itself.
Okay, so we've got this wild possibility of alien life being out there, but they can't just pop over for a visit because of these magic number differences. It's a pretty neat way to address the Fermi paradox, that whole where's everybody question. But the paper doesn't stop there, right? It also looks at how this push-based gravity model might explain some of the biggest mysteries we've got in cosmology, stuff like dark matter and dark energy.
Yep, it goes there. And it proposes some really radical solutions.
Well, I am ready to dive into that rabbit hole. Let's get to those cosmological implications of the Grand Fibonacci theory in the final part of our deep dive. Okay, so we've talked about some pretty wild stuff already, right? Subtle magnetic fields shaping space, gravity as a push, and even aliens that can't visit because their biology would just fall apart.
Yeah, this Grand Fibonacci theory really pushes the boundaries of, well, pretty much everything.
It does. But it doesn't stop there. It also tries to explain some of the biggest mysteries we've got in cosmology, like dark matter and dark energy. Those have been puzzling scientists for decades, haven't they?
Oh yeah, big time. They were basically introduced to explain observations that just didn't fit with our understanding of gravity, like how galaxies rotate way faster than they should based on the amount of stuff we can actually see. And then there's the fact that the expansion of the universe isn't just happening, it's speeding up.
Right, accelerating. So dark matter, they came up with that to be this invisible stuff that provides the extra gravity to hold galaxies together. And dark energy, that's the mysterious force pushing everything apart faster and faster.
Exactly. They're kind of placeholder terms for things we can't directly observe, but whose effects we can see. And get this, they're thought to make up the vast majority of the universe's total energy and matter content.
Yeah.
It's kind of humbling,
It really is. But this paper is saying that maybe, just maybe, this Grand Fibonacci SMF RVS theory can explain those things without needing to invoke dark matter or dark energy at all.
It's a bold claim for sure.
So how does it do that? How do you get rid of dark matter and dark energy with this theory?
Well, it all comes back to that push-based gravity model we were talking about.
Yeah.
Instead of gravity being an attractive force coming from mass, remember, it's a push coming from those interactions between the SMFs and the RVS, those variations in the density of the vacuum.
Okay, yeah, I'm with you. But how does that explain why galaxies are spinning so fast?
So imagine those SMFs, those subtle magnetic fields, they're everywhere, right?
Right.
Pervading all of space, including galaxies. As they interact with the RVS, they create these variations in the vacuum density. And those variations actually contribute to the overall push that stars within the galaxy experience.
So it's not just the visible matter, the stars, gas, dust affecting those stars' movements. There's also this extra push from the SMF-RVS interaction happening within the galaxy.
You got it. And that extra push could explain why we see those super fast rotation speeds without needing to invent dark matter.
Wow, so it just kind of takes care of it.
It's an elegant solution if it holds up, yeah.
Okay, so what about dark energy? How does this theory get rid of that to explain the accelerating expansion?
Well, this is where the fractal nature of the theory really comes in. That Fibonacci fractal scaling. Remember, the same patterns repeating at all these different sizes.
Yeah, it's kind of mind-blowing when you think about it. Like there's this hidden order to everything.
Exactly. And if that scaling also applies to those SMF-RVS interactions, it means the push they generate could actually be increasing over time as the universe expands.
Hold on, so as the universe gets bigger, those SMFs and the RVS have more space to interact, creating a stronger overall push. It's like the universe is not only expanding, but the force pushing it outward is getting stronger too.
That's the idea. And boom, no need for dark energy. It could just be a built-in consequence of how these fundamental things, SMFs, RVS, and that fractal scaling, all interact with each other.
So dark matter, dark energy, this theory is saying they're not really separate things. They're just emerging from a deeper process we haven't fully grasped yet. It's like, I don't know, trying to explain ripples on a pond without knowing there are fish swimming underneath causing those ripples.
I like that analogy. It really gets at how we might be looking at the big picture without understanding the underlying mechanisms.
This has been such a mind trip, honestly. We've gone from tiny atoms to the whole universe, trying to wrap our heads around this one crazy, ambitious theory. It really makes you realize just how much we still don't know about the universe, how much more there is to discover.
You said it. Even if the grand Fibonacci theory isn't completely right, it makes us rethink our assumptions, to think outside the box. Maybe someday this wild idea will be seen as the thing that unlocked a whole new understanding of reality.
That's the beauty of science, right? Always questioning, exploring, never being afraid to challenge what we think we know. Who knows what other amazing discoveries are waiting out there?
Absolutely. So here's something for everyone listening to think about. What other crazy ideas might actually hold the key to solving the universe's biggest mysteries? What seems impossible today might turn out to be the truth tomorrow. That's what makes exploring the universe so exciting.
I love that. Well, that brings us to the end of our deep dive into the grand Fibonacci SMF-RVS theory. A huge thank you to you for sending us this mind-blowing paper and for joining us on this incredible journey.
It was my pleasure. Always happy to talk about these mind-bending ideas.
And to all our listeners out there, keep those curious minds going. If you come across any other wild theories you want us to break down, send them our way. Until next time, keep exploring and keep wondering.